We shall be starting this course in vector spaces 1. We are familiar with the 1, 2, or 3-dimensional vector space. And we are going to see in this chapter, in this study session, how we can also look at things that look like vectors and define them as vectors. We start with the definition of vector space. Given a set V1, V2 up to Vn, which we shall call S, if you add any two vectors in that set together and we get a vector also in that set, this is what we call additivity. And we also multiply by a scalar any vector in the set and still arrive at a vector in the set. This is what we call homogeneity. Once we have additivity and homogeneity, the two major properties of a vector space, we can call that vector space or that space a vector or a linear space. There are other properties. It doesn't matter in which order you add two vectors. It should be V1 plus V2 or V2 plus V1, you arrive at the same answer. So V1 plus V2 is V2 plus V1. Oh, there's a zero vector, zero member of S, such that V plus 0 equals 0 plus V, which is still V. There's an additive inverse V prime, such that V plus V prime is that zero vector. It doesn't matter how we add V1, V2, and V3, because V1 plus V2 plus V3 is equal to V1 plus V2, then plus V3. For all V1, V2, V3 that are in S, that is associativity. The third property is commutativity. Alpha plus beta V equals alpha V plus beta V for all V in S. And alpha beta V is alpha into beta V for all V in S. 1V is V. Alpha into V1 plus V2 is alpha V1 plus alpha V2, not beta V2, for V1, V2 in S and alpha in K. Alpha and beta are in K, where K is a field. The fields we are going to deal with in this course are the real number line R and the complex plane C. Then S is called a vector space or a linear space once all these conditions are satisfied. The vector space is a real vector space if K is R, or a complex vector space if K is C. As we said earlier, the vector spaces we shall come across in our study are such that we shall be bothered with only the first two properties of a vector space, that is additivity and homogeneity. So you may as well get used to this slogan: additivity plus homogeneity equals linearity. So we're going to take some examples. Show that the set of Cartesian vectors in 3 dimensions, V3, is a real vector space. A and B are in V3, and lambda is in R. When you add two such vectors, what you get will also be in V3, because when you add two vectors in 3 dimensions, you can only get a vector in 3 dimensions, not a vector in 4 dimensions. Multiply a 3-dimensional vector by a scalar constant, you can only get a vector in 3 dimensions, not a vector in 4 dimensions or 5 dimensions. It is clear that all other conditions are also satisfied. Example 2, prove that the set of m by n matrices under matrix addition and scalar multiplication, that is MMN, denoted MMN, is a vector space over the real numbers or the complex plane. Now assume A and B are in MMN and lambda is in RC. When you add two m by n matrices, won't you get an m by n matrix? Possible. So A plus B is also in MMN. Multiply an m by n matrix by a scalar constant. What you get will also be an m by n matrix. Will you get a dimension other than that? No. Other conditions are also satisfied by vectors in MMN. Indeed, the zero vector OMN is the m by n matrix that has all its entries 0. That is also in MMN because it's still an m by n matrix. And the vector minus m is the additive inverse of the vector m, which is also in MMN. Example 3. A set A of x, g of x, which we shall call, and so on, which we shall call f, of square integrable functions of x over the interval a, b. f of x, g of x, and so on and so forth, and f. Lambda is in R or C. That is the real or complex valued function, such that integral from a to b of f modulus of f x squared dx is less than infinity. That is, it is finite. You're going to see why we require that this integral be finite. The sum of two such functions is also a square integrable function of x over the interval. Likewise, the scalar multiplication of any such a function. All other conditions are satisfied by vector sin and f. The zero vector is the vector r of x equals identically is equal to 0, and the zero valued function, which is also in f. The vector minus s of x is the additive inverse of the vector s of x. If s of x is square integrable, then minus s of x is also square integrable. Indeed, the two integrals should be the same. Now let us move on to linear independence. Suppose you are given a set vi I equals 1 to n. You can write alpha a1 plus b1 plus a to b2 up to plus a and bn equals 0. And this implies that a1, a2, and all the a's, other a's are 0. So we say that vi I equals 1 to n is a linearly independent set. If even just one of them is non-zero, the set is linearly dependent. Of course, when you look at a vector in two dimensions, let's say you have alpha I plus beta j. If that is equal to 0, then both alpha and beta must be 0. Because if only alpha is 0, you still have got beta j. If only beta was 0, then you'd have got alpha I. If that vector is 0, then both components must be 0. Check if the set I to I j is linearly independent. We form the linear expression C1 phi 1 plus C2 phi 2 plus C3 phi 3 equals 0. Where phi 1 is I, phi 2 is 2I, please, not 2j. And phi 3 is j. Thus, I C1 plus 2I C2 plus j C3 equals 0. And collect like terms. I into C1 plus 2C2 plus j C3 equals 0, which implies that C1 plus 2C2 is 0. And C3 equals 0. We see that C1 equals minus 2C2 and C3 equals 0. You can see that C1 and C2 do not necessarily have to be 0. Because suppose C2 is 1, then C1 will be minus 2. And you still get that expression in equation 319. It means that C1 and C2 do not necessarily have to be 0. The vectors are linearly dependent. Is the set 1x squared linearly independent? Let us pick vectors P1, P2, and P3. Then A1, P1 plus A2, P2 plus A3, P3 equals 0. Where P1 is 1, P2 is x, and P3 is x squared. We're going to get A11 plus A2x plus A3x squared equals 0. If you equate coefficients of x on both sides, that is coefficient of x to the power 0, x to the power 1, and x to the power 2 independently, we're going to get A1 equals A2 equals A3 equals 0, which means that the vectors are linearly independent. We wish to write any vector in one, let's say, x direction. You need only one unit vector. Any two vectors in the x direction must be linearly dependent, but we can write as one as A1I, the other one as A2I, where A1 and A2 are scalars. So that any two vectors in the vector space of one-dimensional vectors are linearly dependent. We have seen something like this before. Let the two vectors be A1I and the other one and A2I. We form the linear combination C1 A1I plus C2 A2I equals 0, where A1 and A2 are scalar constants. Obviously, C1 and C2 need not be identically 0 for the equation to hold, for C1 equals minus C2 A2 over A1 will also satisfy the expression. We conclude therefore that the vectors must be linearly dependent. In general, any n plus 1 vectors in an n-dimensional space must be linearly dependent. 3.3, let's look at span. If you can express any vector in a vector space as a linear combination of a set of vectors, E1, E2 up to En, then we say the vector space V is spanned by the set of vectors E1, E2 up to En. Thus, the set of all linear combinations of vectors in the set E1, E2 up to En is said to be span of the vector space V. That set is said to be a basis for V. Thus, a set of n linearly independent vectors that span V is a basis for V. However, you can also span the same vector space with another set of n plus k vectors with k an integer greater than 0. However, the vectors will not be linearly dependent, as we have seen in ITQ. Indeed, the coefficient Ci of the summation I equals 1 to m, Ci, Ei will not be unique basis vector. Let V be an n-dimensional vector space. Any set of n linearly independent vectors E1, E2 up to En forms a basis for V. Then each vector Ei is called a basis vector for the vector space. Given such a basis, any vector V in V can be expressed uniquely, the linear combination of the vectors E1, E2 up to En. That is, x equals x1 E1 plus x to E2 up to plus xn En. Just the way you express vector 3, 4 as 3i plus 4j. I is E1, j is E2. Note that the basis vectors do not have to be unit vectors. Neither must they be mutually at right angle. That is the end of study session. Study session 4, vector spaces 2. Let's go straight to the practice of an inner product. Let V be a vector space, real or complex. Then the inner product of V and W that are in V, which we write as bracket opens V, comma, W, bracket closes, has the following properties. 1. The inner product of a vector with itself must be greater than or equal to 0. 2. That inner product with vector with itself is 0 if and only if V itself is 0. VW equals WV, that is symmetry. CVW equals C star VW, and VCW equals CVW, that is, if C is attached to the first member of that inner product, it comes out with a star. If it's attached to the second member of the inner product, it comes out without a star. But star is complex conjugation. 5. VW plus Z is VW plus VZ. And lastly, VW is less than or equal to norm of V, norm of W. I considered it twice before choosing to introduce norm before getting to where it is defined, but we have no choice but to bring this in at this stage. Prove the Cauchy-Schwarz inequality for any inner product. To prove that inequality, we write for an arbitrarity in R, the real number. 0 is less than or equal to norm of V plus TW squared. And that in itself is defined as VTW, that is inner product of V and TW squared, which will be VV plus TW plus 2T into VW, which is defined as R of T, because it's a function of T. So 0 is less than or equal to norm of V squared plus T squared, norm of W squared, plus 2T inner product of V and W. We differentiate the right-hand side with respect to T and equate to 0 because we're trying to find the minimum value of R of T. And R of T being the quadratic function increasing upwards since P of T is greater than or equal to 0. You carry out that differentiation. You define P of T as that expression on the right in the last expression on this page. So 0 will be equal to 2T norm of W squared plus 2 inner product of V W. The differential of norm of V squared is, of course, 0. From this, we get T equals minus the inner product of V and W divided by norm of W squared. Hence, put this into our expression. 0 less than, this is the last expression on this page. We're going to arrive at 0 less than equal to norm of V squared plus minus inner product of V and W over norm of W all squared, norm of W squared, plus 2 into minus V, inner product of V and W over norm of W squared, then V, inner product of V and W. If we rearrange that, you arrive at 0 less than equal to norm of V squared plus V W, that's in the inner product of V and W squared, over norm of W squared, minus 2 inner product of VW squared over norm of W squared, which will be equal to norm of V squared minus VW, that is the inner product of V and W squared, over norm of W squared. Therefore, the inner product of VW squared is less than or equal to norm of V squared, norm of W squared. If you take the positive square root of both sides, the inner product of V and W will be less than or equal to norm of V, norm of W. Note that we did not have to make recourse to the exact definition of the inner product. As such, every inner product satisfies the equation was inequality, because as you can see, we only made use of the definition of the inner product. Example, given the vectors A and B in 3 dimensions, we define the inner product as AB equals A transpose B. This is what you have been familiar with all along, where A transpose is the transpose of the line matrix representing A. Thus, if A is 1, 0, 1 and B is 2, 1, 1, then inner product of A and B will be equal to 1, 0, 1, the row matrix, 2, 1, 1 is a column matrix. What you get is 3. Show that the inner product of B and W is defined as summation I equals 1 to N, which is VIWI is an inner product on Rn. That means it must satisfy the conditions for an inner product. So 1, VV is the summation I equals 1 to N, VI, summation I equals 1 to N, VI squared. Obviously, the sum of squares of numbers must be greater than or equal to 0. It will be 0 only if V itself is 0, which is 2. 3. VW equals summation I equals 1 to N, VIWI. Since we are dealing with only scalars, you can also arrange to have WI first and VI first, and VI coming later. Note that VI and WI are scalars. They are the components of the vectors V and W respectively. CVW is summation I equals 1 to N, C star VIWI, which is C star summation I equals 1 to N, VIWI, which is C star VW. There's a similar expression for VCW. 4. VW plus Z is summation I equals 1 to N, VIW plus ZI, which is summation I equals 1 to N, VI into WI plus ZI. When you see W plus Z, W plus Z added together, then I outside, means that the ith component of the sum, vector sum of W and Z, which is what you have on the right hand side. So this will be equal to VW plus VZ. Hence, VW, which is summation I equals 1 to N, VIW is an inner product on Rn. Example 2. The space of n by n matrices, the inner product of A and B in MMN is defined as AB equals trace of A dagger B. A dagger is the transpose of A and then the complex conjugation of every element of that matrix. Or we first take the complex conjugation and then we transpose the matrix. Trace of P is the trace of the matrix P, which is the sum of the diagonal elements of P. Of course, P must be a square matrix, that is, the number of columns must be equal to the number of rows. So let A be equal to I0, 1, 1, and B be equal to 0 minus I, 1, 0. The A transpose will be I1, 0, 1. We take the complex conjugate of that to get minus I1, 0, 1. So A dagger B, which is A transpose bar B, will be equal to minus I1, 0, 1, 0 minus I1, 0. We get 1 minus 1, 1, 0. The trace of that will be equal to 1 plus 0, which is 1. Find the inner product of AB in Mn if A is this and B is that. A transpose B will be equal to that. Then you take the transpose of that. I believe everybody in this class can take the inner product of any two vectors. You can take the product of two matrices. The trace of that matrix is 8. Example 3, the space of square integrable complex value functions fx over the interval a, b, that is, f of x is in fx, implies, that's s, small s, implies that graph from a to b of modulus of f of x, modulus of x squared dx is less than infinity. So we define the inner product on this space as inner product fg equals integral from a to b, f star of x, g of x dx, where f star of x is the complex conjugate of f of x. Let's see an example of that. Suppose we are given f of x equals 2x plus I, and g of x equals 5x minus 2ix, both belonging to the vector space of real valued functions of x for x between 0 and 2. 1, normalize f of x, and 2, find the inner product of the functions. The normalization of the first one is what we are going to see first. Integral from 0 to 2 of af star of x, af of x dx equals a squared, integral from 0 to 2 of 2x minus I, 2x plus I dx. That will be equal to a squared, integral from 0 to 2 of 4x squared plus 1 dx. I believe we can all carry out that integration and arrive at, put the limits and arrive at 38 over 3a squared equals 1. So we make the solve for a. So a is square root of 3 over 38. Therefore, the normalized function is square root of 3 over 38, 2x plus I. The inner product of f and g is integral from 0 to 2, f star of x, g of x, but the x is missing. You must always put the x or the whatever you are integrating with respect to. This will be equal to integral from 0 to 2, 2x plus I into 5x minus 2ix. The x is also missing. Equals integral from 0 to 2, 10x squared minus 4ix plus 5ix plus 2i squared x dx. That gives you integral from 0 to 2, 10x squared plus ix minus 2x dx. If you carry out that integration, you arrive at 68 over 3 plus 4i. Let x be a vector space over K, the real or the complex number field. A real valued function norm on x is a norm on x, that is, it takes the vector space to R. It takes vectors from the vector space to R if and only if the following conditions are satisfied. Norm of x is greater than or equal to 0. Norm of x is 0 if and only if x itself is 0. Norm of x plus y is less than or equal to norm of x plus norm of y. That is triangle inequality, which says that no single side of a triangle can be longer than the sum of the remaining two sides. The best you can have is that the norm of x plus y will be equal to norm of x plus norm of y, which means that the norm itself is on, that means x and y are in the same direction. Norm of alpha x is absolute value of alpha, norm of x, for all x in x and alpha in C. The norm of a vector is its distance in quotes from the origin. There are many ways of defining a norm on a vector space. In the case where x is R, the real number line, the absolute value norm is the absolute value of x. This is the distance from the origin. Euclidean norm on the n-dimensional Euclidean space is norm of x equals square root of x1 squared plus x2 squared up to plus xn squared. You are more familiar with that. More generally, the LP norm is defined on a class of spaces called LP spaces and is defined as norm over P equals absolute x1 to the power P plus absolute x2 to the power P up to plus absolute xn to the power P. For you to have the dimension of x, we must find the pth root. That's why everything is raised to power 1 over P. You can then see that the Euclidean norm is the L2 space, and the L2 norm is norm of 2, which is equal to absolute value of x1 squared plus absolute value of x2 squared up to plus absolute value of xn squared, all raised to power half. The n-dimensional complex space has the norm of z equals square root of z1 modulo squared plus z2 modulo squared up to plus zn modulo squared, which is square root of z1 z bar, z1 bar plus z2 bar plus up to zn bar. The max norm on a finite dimensional space is defined as norm infinite equals max of x, modulus of x1, modulus of x2 up to modulus of xn, which is the largest absolute value of component of x, where x is x1, x2, up to xn. Prove that the triangle inequality holds for any norm. Norm of x plus y squared is x plus y, the inner product of x plus y, which is 7. That will be norm of x squared plus norm of y squared plus 2 inner product of x, y. That, of course, will be less than or equal to norm of x squared plus norm of y squared plus 2 absolute value of inner product of x and y. Because the absolute value of x, inner product of x plus y, is going to be greater than or equal to the inner product of x and y. Don't forget that x and y can even be, inner product can be negative. But from Cauchy-Schwarz inequality, inner product of x, y is less than or equal to norm of x, norm of y. Hence, norm of x plus y all squared, which we have defined, everything follows from what we have seen so far. So we are just repeating that line. Then less than or equal to norm of x squared plus norm of y squared plus 2 inner product of x, y, less than or equal to norm of x squared plus norm of y squared plus 2 norm of x, norm of y, which is equal to, when you put all that together, that is norm of x plus norm of y all squared. If you take the positive square root of both sides as a norm of the positive, then we have proven the triangle inequality. If the norm of V in the vector space V is unity, such a vector is said to be normalized. In any case, even if a vector is not normalized, we can normalize it by dividing by its norm. In physics, the most commonly used norm is the one induced by the inner product, and this is the one which shall be concerning ourselves with. The Euclidean norm is an example of such a norm. In that case, norm of A is square root of the inner product of A with itself. We shall illustrate with 3 cases. Case 1, given the vector A in V3, the norm of A is square root of the inner product of A with itself. See an example now. A equals 1, 0, 1. To find this norm, we multiply by the same vector. But of course, the first one is going to now be a row vector, and the second one a column vector. We're going to arrive at 2. So norm of A is the square root of inner product, which is square root of 2. We see that A is not normalized. However, C, which is defined as A over norm of A, which is 1 over root 2, 101 is normalized. You can check this on your own. Case 2, the space of n by n matrices. Even the n by n matrix A, the norm of A is defined as norm of A equals square root of trace of A with itself, inner product of A with itself. As an example, let us normalize A, which is I0, 1, 1. The transpose is I101, and the complex conjugate of that is going to be minus I101. So A dagger A, what you have there is going to give you 2, 1, 1, 1. The trace of that is 2 plus 1, which is 3. Therefore, the norm of A is square root of 3. You can see A is non-normalized. But if you define C as A over norm of A, which is 1 over root 3, I011, then it will be normalized. Case 3, the space of square integrable complex valued functions fs over the interval AB. Let f of x be in that space. Then the norm of f is the square root of the inner product of f itself, where the latter is integral from A to B of modulus of f of x squared. Yes. You can now see why we have to deal with square integrable functions. Because if f is non-normalized and you divide by the norm, if the norm is infinite, then the new function I'm defining is actually 0. So f might not be normalized, but h, which is f over norm of f, is normalized. F is said to be normalizable. If, for instance, the function is not square integrable, that will mean that we'll be dividing f by an infinite number. You see, such a function is not normalizable. Find the norm of g of x equals 5x minus 2ix. Hence, normalize the function. The norm of g of x is defined as, we have seen that before. That's going to be square root of integral from 0 to 2 g star of x, g of x dx, which will be square root of integral from 0 to 2 of 5x minus 2ix into 5x plus 2ix dx, which will be equal to integral from 0 to 2, 29x squared dx, which is 29 over 3x cubic from 0 to 2, which is 232 over 3. The normalized function is therefore g of x over norm of g of x, which is 5x minus 2ix over square root of 232 over 3, which is square root of 3 over 232, 5x minus 2ix. We now move on to study section 5, orthogonal matrices. A matrix Q such that QA, QB, that is inner product of Q and QB, is still A inner product of A and B. That is, this particular matrix preserves inner product for all A and B in the vector space. The set of n Euclidean vectors is called an orthogonal matrix. That is, a matrix Q such that this holds, where E is the set of n-dimensional Euclidean vectors, is called an orthogonal matrix. That means that there should be a comma after Euclidean vectors. In other words, an orthogonal matrix preserves the inner product of two Euclidean vectors. You should find this interesting. It means the inner product remains the same in the two different coordinate systems. That this Q could be a transformation from one coordinate system to another. If one of them is got by rotating the other one about one axis. Remember we said, and we soon show, that the rotation matrix is an orthogonal matrix. Since QA, QB is B, Q transpose QA, which is B, Q transpose QA. Once Q leaves A and goes to B, it must carry transpose, and vice versa. The necessary and sufficient condition for Q to be orthogonal is that Q transpose be the identity matrix, because in that case, B, Q transpose Q will be B, A. Or equivalently, by multiplying on the left by Q inverse, Q inverse Q transpose will be equal to Q inverse I. On the left, Q inverse Q will be equal to the identity matrix. When that multiplies Q transpose, you still get Q transpose. Because when the identity matrix multiplies any matrix, you still get that same matrix. It is playing the role of one in normal, usual multiplication. So Q transpose is equal to Q inverse. This is particularly interesting. So in other words, if you are given an orthogonal matrix, instead of looking for the inverse, just transpose it. Transpose is much easier than finding the inverse of the matrix. Note that determinant of Q transpose is determinant of Q transpose, since determinant of A, B is determinant of A, determinant of B. So determinant of Q transpose will be called determinant of Q, since determinant of A transpose is determinant of A. So you get determinant of Q all squared. And since we said Q transpose itself is the identity matrix, that means the determinant of Q all squared is determinant of I, which is equal to 1. The determinant of an identity matrix is 1. Hence, determinant of Q is plus or minus 1. We take the square root of that expression. Q is said to be a proper orthogonal matrix if determinant of Q is 1, and an improper orthogonal matrix if determinant of Q is minus 1. If determinant is equal to 1, then determinant of Q minus I, determinant of Q minus I, determinant of Q transpose. Since determinant of Q is 1, what we have done is just multiply by 1. We can now make use of the property of determinant of A, determinant of B equals determinant of AB to get determinant of Q transpose minus Q transpose. But what is Q transpose? That's the identity matrix. So this will be equal to determinant of I minus Q transpose. Since Q transpose, as I said, is equal to the identity matrix. This will be equal to determinant of I transpose minus Q transpose, because when you take the transpose of I minus Q transpose, you still get the same determinant. So since determinant of A transpose is determinant of A, so this will be equal to plus determinant of I minus Q, because I transpose is I, and Q transpose is still Q. When you transpose twice, you get the original matrix again. So this is equal to minus determinant of Q minus I. We rearrange to make Q come first. We do that, minus will go out, multiply from outside. Since determinant of A minus B minus determinant of B minus A. Now we are saying determinant of Q minus I equals minus determinant of Q minus I. We are saying X equals minus X, which implies that X must be 0. Therefore, 1 is an eigenvalue, so that there exists E3 such that Q E3 equals 1 E3, which is E3. Because once you say determinant of Q minus I equals 0, you take your mind back to eigenvalue equations. It means that Q minus lambda I, determinant of Q minus lambda I equals 0, when lambda in this case must be 1. That's why we are saying that lambda, is the eigenvalue. So 1 is the eigenvalue in this case. And it is such that Q E3 equals 1 E3, which is E3. Let us choose E1, E2 to be orthonormal to E3. Then E3 could be the unit vector K. Then E1 and E2 could be I and J respectively. In terms of this basis, we have Q equals A, B, 0, C, D, 0, 0, 0, 1. The transpose of that will be A, C, 0, B, G, 0, 0, 0, 1. So Q transpose will be, which you know is the identity matrix, will be equal to A squared plus B squared, AC plus BD 0, CA plus BD, C squared plus D squared 0, and 0, 0, 1. Which means that since if two matrices are the same, then corresponding elements are the same. So A squared plus B squared is 1, which is also equal to C squared plus D squared. AC plus BD is 0, which is also equal to CA plus BD. Also, determinant of Q is 1. We knew that all along. And determinant of Q or Q transpose is AD minus AC. So from equation 2, B, equation 2 will be 5 and 16. 516. You can take BD plus AC equals 0. That's the first one, 516. Putting this in 3, 3 will be the equation that has plus in between. It's AC plus BD. Okay, A squared plus B squared equals 1. Or let's say AD plus AD minus ABC equals 1. That is 517. Is what we're referring to as 3 now. You get AD plus AC squared by D equals 1, which implies that A into C squared plus D squared equals D, which implies that A equals G. Use A equals D in equation 2 to get C equals minus B. Therefore, Q is equal to AB0 minus BA0, 0, 0, 1, with A squared plus B squared being equal to 1, as we saw in equation 515. Since you have A squared plus B squared equals 1, that brings to mind that A could be cos theta and B could be sin theta, since cos squared theta plus sin squared theta equals 1. So Q is cos theta, sin theta, minus sin theta, cos theta, 0, 0, 0, 0. What is the interpretation? This corresponds to a rotation about an axis perpendicular to E3. Okay. Improper orthogonal matrices have one determinant minus 1 and are equivalent to a reflection combined with a proper rotation. Note that only proper orthogonal matrices represent rotations. In addition, the direction and axis of rotation is not as simple in all cases as in the example we have seen. To state without proof is rotation matrix theorem. 1. Rotation matrices are orthogonal matrices with unit determinants. That is, with determinant equal to plus 1. Rotation matrix A that is not the identity matrix, i.e., a non-trivial rotation matrix, has eigenvalues 1, e to I theta, and e to minus I theta. The eigenvector corresponding to the eigenvalue 1 is a line. This is the eigenvector that determines the axis of rotation, as it is invariant with respect to the rotation. Hence, AE equals 1E, which is E, which we have seen before. The axis of rotation is the line in 3, that is Roman 3, and is determined from A minus IU equals 0, since this is the matrix equation for eigenvalue 1. And the angle of rotation is the angle measured anticlockwise when V cross AV points in your direction, where V is any vector in the plane perpendicular to the axis of rotation. 5. The angle of rotation can be obtained from cos theta equals half into trace of A minus 1 up to sine. Show that root 4 trivially gives us the same angle as is used in the matrix in equation 522. And this is the solution. A equals that half trace of A minus 1 is half into 2 cos theta plus 1 minus 1, which is cos theta, meaning the angle of rotation is the same as theta in the matrix. Confirm the matrix A equals cos theta sin theta 0, sin theta minus cos theta 0, 0, 0, minus 1 is a rotation matrix. Also show that irrespective of the angle theta, the rotation angle is pi. A transpose is that, which gives you the identity matrix. Therefore, it is the rotation matrix. The determinant of the matrix is minus 1 times minus cos theta minus sin theta, which is 1. Using the last row because of the ease it offers us, having only one non-zero element. So you can find the determinant of a matrix using any row or any column. So we chose the easiest. So the matrix is orthogonal and has the determinant 1. It's a proper orthogonal matrix, the rotation matrix. To find the axis of rotation, we solve A minus IU equals 0. So cos theta, sin theta minus cos theta 0, 0, 0, 0, 1 minus 1 minus 1, 0, 0, 0, 1, 0, 0, 0, 1 u1, u2 up to u3 equals 1 minus cos theta minus sin theta 0 minus sin theta 1 plus cos theta 0, 0, 0, 2. So the axis is given by u1 into 1 minus cos theta minus u2 sin theta equals 0. Or minus u1 sin theta plus u2 into 1 plus cos theta equals 0. So the axis is sin theta 1 minus cos theta 0. Or 1 plus cos theta sin theta 0. Notice that this is not the z axis. This is partly because A33 is not equal to 1. The angle of rotation is half into trace of A minus 1, which is half into cos theta minus 1 minus 1, which is minus 1. Hence, theta is not the angle of rotation. With respect of the angle theta, the angle of rotation is arc cos of minus 1, which is pi. The matrix 1 over 25, 9, 12, minus 20, minus 20, 15, 0, 12, 16, 15 is a proper orthogonal matrix. Find the angle, find the axis and angle of rotation. So A is as given. The axis is given by A minus IU, which is what you have there. I'm sure everybody can figure that out. You arrive at minus 16u1 plus 12u2 minus 20u3 equals 0. Minus 20u1 minus 10u2 equals 0. 12u1 minus plus 16u2 plus 10u3 equals 0. You can simplify that to arrive at minus 4u1 plus 3u2 minus 5u3 equals 0. 2u1 plus u2 equals 0. 6u1 plus 8u2 plus 5u3 equals 0. Or u2 equals minus 2u1 minus 4u1 plus 3 to minus 2u1 minus 5u3 equals 0. Minus 5u3 equals 10u1. u3 equals minus 2u1. So just choose one to be u1 to be 1, and the other ones will follow accordingly. If u1 is 1, u3 will be minus 2u1, which is minus 2. And u3 also becomes minus 2u1, which is minus 2. The angle of rotation is given by cos theta equals half into trace of A minus 1. Put all that together and arrive at 7 over 25. It means that theta is 73.74 degrees. What is the motivation? Why are we so interested in orthogonal matrices? If Q is an orthogonal matrix, then its rows are an orthonormal set. In addition, its columns are also an orthonormal set. Show that the following is an orthogonal matrix. Q equals, all you need to do is just find Q transpose and get the identity matrix. Hence, Q is an orthogonal matrix. You can verify that the columns are orthonormal. You can also show that the rows are orthonormal. Change of basis. We are quite familiar with the usual basis in the Euclidean plane, I and J. We can write this as 1, 0, and 0, 1. You can also show that 1, 1, and minus 1 minus 1 is also a basis for the Euclidean plane. These vectors are respectively I plus j and I minus j. We see that the basis for a vector space is not unique. You can easily construct a linear map. This is a matrix that takes the basis vector in one basis. So let us consider Rn as a vector space. Let I equals 1 to n be a basis in the vector space. We can write any vector A in the vector space as A1, A2 up to AN equals C1, U1 plus C2, U2 up to plus CN, UN. Now, U1 has components U11, U12, U12, U13, and so on up to U12. You're going to write C1 and all the components vertically, plus C2, all the components of U2 vertically, up to plus CN, UN1 up to UNN. You carry out the expansion. You arrive at A1 equals C1, U11, C2 plus C2, U2 plus CN, UN1. A2 is C1, U12 plus C2, U22 up to plus CN, UN2. Down to AN equals C1, U1 plus C2, U2, up to plus CN, UNN. So as A1, A2 up to AN equals U11, U21, UN1, then U12, on and on like that, then C1, C2 up to CN. Notice that matrix U11, U21 is not as you usually find a matrix. U11, U12 should have been horizontally arranged, but in this case, it is not so because vectors are arranged vertically. So that means you can write A1, A2 up to AN as B, C1, C2 up to CN, where B is the matrix shown in equation 525, which is formed from the vectors U1, U2 up to UN arranged vertically. Follows immediately that we can write by multiplying both sides by B inverse. To multiply 526 by B inverse, get B inverse A1, A2 up to AN equals B inverse B, C1, C2 up to CN. B inverse B is the identity matrix. So if you swap left and right, we are going to arrive at C1, C2 up to CN equals B inverse A1, A2 up to AN. But you might as well have written A right away in another basis, B, J equals 120. Since we said the basis of a vector space is not unique. So A1, A2 up to AN is D1, V1, plus D2, V2, up to plus DN, VN, which is V11, V21, and so on and so forth. You can write that now. That will be D, D1, D2, up to DN, where D is the matrix shown in 528. Therefore, equation 526 is C1, C2 up to CN equals B inverse A1, A2 up to AN. But don't forget that A1, A2 up to AN itself is D, D1, D2 up to DN. That's equation 528. Conversely, D1, D2 up to DN is D inverse B, C1, C2 up to CN. That should be easy for you to figure out. Look at C1, C2 up to CN being equal to B inverse D, D1, D2 up to DN. You multiply both sides by B. You get B, C1, that is C1, C2 up to CN in 530, multiply on the left by B. You get B, C1, C2 up to CN equals B, B inverse. B inverse will give you identity matrix. Then you are left with D, D1, D2 up to DN. Now to get D1, D2 up to DN, that means you have to multiply both sides by D inverse. D inverse D will give you the identity matrix. So you are left with only D1, D2 up to DN on your right. And on your left, you now have D inverse B. We swapped left for right to arrive at D1, D2 up to DN equals D inverse B, C1, C2 up to CN. As an example, given the basis 2, 3, 1, 4, write the matrix that will transform this basis to the basis 0, 2, minus 1, 5. What are the coordinates of the vector 2, 6 in the new basis? B is that we arrange the basis vectors vertically 2, 3, 1, 4. Likewise, D 0, 2, minus 1, 5. So B inverse, you know how to find the inverse of a two-dimensional matrix, 2 by 2 matrix. We find the determinant, we take it to the denominator, then swap the elements on the main diagonal, and then multiply the off diagonal or the elements in the other diagonal by minus, each of the elements by minus. Likewise, D inverse is that. So B inverse D is 1 over 5 into minus 2, minus 9, 4, 13. The matrix of transformation is D inverse B, which is half into 5, 1, minus 2, 0, 2, 1, 3, 4, which is 1 over 2, 13, 9, minus 4, minus 2. We apply this to vector 2, 6. We arrive at D1, D2 equals D inverse B, C1, C2, which is half into 13 minus 4, 9 minus 2, minus 2, 6, which is half 28 minus 4, which is 14 minus 2. Check, you can check if you are right by going back the other way. C1, C2 is B inverse D, D1, D2, which is 1 over 5 minus 2 minus 9, 4, 13. Applied to 14 minus 2. We arrive at what we started with again, minus 2, 6. So we covered the original coordinates in the first basis. We will stop here for now. In the next class, we are going to look at orthogonality and orthonormality.